ME 347, Example 1, Finite or Integral Control Volume Analysis of Developing Laminar Flow Between Parallel Plates. Water flows into a wide channel with a height of twice h through a well-rounded inlet as shown. The uniform velocity magnitude at the channel entrance is 0.10 meters per second at section 1. The velocity distribution is specified for section 2 downstream. For part A, evaluate the maximum velocity used to define the velocity distribution at section 2. For part B, calculate the pressure drop along the channel due to the change in momentum of the fluid from section 1 to section 2. For part C, discuss if the pressure drop would be higher or lower if friction is accounted for. For this problem, we first assume flow of a Newtonian fluid with constant properties. Second, we assume steady two-dimensional flow in the xy plane for a wide channel in the z direction compared to the height in the y direction. Thus, we are assuming for the majority of the channel width there are negligible end effects. This is commonly referred to as flow between parallel plates. Also, note that for the flow at the outlet, the velocity only depends on the y direction. Thus, it is now one-dimensional. This is called fully developed flow. However, to get to this profile, it needed to go to 0 at the walls by the no-slip condition, while speeding up in the center, which requires that the flow be two-dimensional. This is called the entry region. Third, for our well-rounded inlet, we assume that the flow is uniform at section 1. Fourth, we assume negligible end effects due to gravity. For part A, evaluate the maximum velocity at section 2. Because we are solving for an unknown velocity, we need to apply conservation of mass. Also, since we are already given the velocity distribution at the exit, we can use an integral analysis to solve for our single unknown maximum velocity. Thus, we apply conservation of mass to a finite control volume from section 1 to section 2. The first term on the left gives the rate of change of mass within the control volume. For steady flow that does not change with time, this term is 0. The second term on the left gives the net rate at which mass crosses the boundaries of our control volume, or control surfaces. We expand this term by integrating over the boundaries, which include the inlet at section 1, the outlet at section 2, and the top and bottom walls at y equals plus and minus h. Note that for incompressible flow, the constant density can be brought outside the area integral and canceled. Also, there is no flow across the walls, thus the last term on the left is 0. For the first term on the left, the dot product of the velocity vector with the outward unit normal at section 1 gives negative capital U. Because capital U is constant, the area integral is just twice h times b, the width of the channel. For the second term on the left, the dot product of the velocity vector with the outward unit normal at section 2 is now positive. In general, the dot product is always negative for inflow and positive for outflow by definition. This time, because the velocity distribution depends on y, it must be integrated from y equals minus h to h. Because the profile is symmetric about 0, we can multiply by 2 and integrate from 0 to h. We also integrate from z equals 0 to b, which reduces to just b because the velocity is not changing in the z direction. We can cancel the b term as expected for our two-dimensional flow. Simplifying, we get that the maximum velocity is 3/2 times the uniform velocity at the inlet. For our case, that equals 0.15 meters per second. Alternatively, for Part A, we can start from a simplified form of conservation of mass for an incompressible fluid, where the sum of all the volumetric flow rates into and out of a control volume are equal to 0, where the volumetric flow rate is obtained by integrating over the component of the velocity vector normal to an area. For the same control volume, we account for the flow rate at section 1 and the flow rate out at section 2 to get the same equation from our previous analysis. Thus, this method, of course, leads to the same result. For Part B, calculate the pressure drop along the channel due to the change of momentum of the fluid from section 1 to section 2. Because we are solving for a force per unit area, we need to apply conservation of momentum. Also, since it is an overall force, we can use an integral analysis to solve for our single unknown pressure drop. Thus, we apply the momentum equation to a finite control volume from section 1 to section 2. This is a vector equation with 3 components. Because we want to solve for the pressure drop in the x direction, we will use the x component of this equation, where u is the x component of the velocity vector. The first term on the left gives the rate of change of momentum within the control volume. For steady flow that does not change with time, this term is 0. The second term on the left gives the net rate at which momentum crosses the boundaries of our control volume or control surfaces. We expand this term by integrating over all the boundaries, which include the inlet at section 1, the outlet at section 2, and the top and bottom walls at y equals plus and minus h. Since there is no flow across the walls, the third term on the left is 0. The term on the right gives the sum of all the forces acting on the control volume in the x direction. For the first term on the left, the dot product of the velocity vector with the outward unit normal at section 1 gives negative capital U. Because capital U and density are constant, the area integral is just twice h times b. For the second term on the left, the dot product of the velocity vector with the outward unit normal at section 2 is positive. Again, because the velocity distribution depends on y, it must be integrated from y equals minus h to h, but we can bring the constant density and maximum velocity out of the integral. Because the profile is symmetric about 0, we can multiply by 2 and integrate from 0 to h. We also integrate from z equals 0 to b, which reduces to b because the velocity is not changing in the z direction. For the right side, we must include all the surface forces acting on the control surfaces and all the body forces acting on the control volume. The first surface force we include is the pressure acting at section 1 and section 2 on the cross-sectional area of twice h times b. Note that the sign convention for pressure is that it is always acting inwards on our control volume. Also note that for a static fluid, pressure and normal stress have the same magnitude but opposite sign convention. The second surface force we include is the shear stress due to fluid friction or viscosity, acting on the wall area of twice b times L, the length between section 1 and 2. Note that the force due to friction acts in the negative x direction because it opposes the fluid motion. Finally, we include a term for a body force due to gravity, but cross it out because we assume it is negligible compared to the other terms. We then integrate and simplify the equation as shown. Note that once again, for our two-dimensional flow, the width b does cancel as expected. Finally, we get that the pressure drop in the channel has two components. The first term on the right is a force due to friction, and the second term on the right is due to the change of momentum for the flow that accelerated in the center and slowed down at the walls. For part B, we are only solving for the second component, so we evaluate this term to get that the pressure drop due to the change in the fluid momentum is 2.0 pascals. For part C, discuss if the pressure drop would be higher or lower if friction is accounted for. Looking back at our result for part B, we see that if we account for the friction term, that the calculated pressure drop would be higher. This makes sense because there would be an additional pressure force to overcome the force due to friction to push the flow through the channel. Furthermore, we note that if the flow continues after section 2, it has become fully developed with a velocity profile that no longer depends on the x direction. Thus, the momentum is no longer changing, and the net force due to pressure is just equal to the force required to overcome friction. The ratio of L over H accounts for the fact that the pressure acts on the cross-sectional area while the friction acts on the wall area.